Hey everyone, welcome to today's lesson. Today we are on lesson 1-5, and in this lesson what we are going to learn is to determine whether a function is one-to-one. Our language objective is to explain how we determine whether a given function is one-to-one. So let's take a look at our do now. Hey everyone, so let's take a look at our do now, and we are given two composition questions to do. So I want you guys to pause the video, try both of these out, and we will get back together when you guys finish. Okay, so here are my two answers. For number one, we start off with the f function. We input the given original input of -4n. We get an output of -4n minus 1. That is our new input for our second function, which is g. I input that into my second function. I do my algebra, and I end up at 64n squared plus 32n plus 4. For number two, we do pretty much the same thing. We start off with our original input of p minus 3. I input that into the g function. I do my algebra. I get some quadratic. That quadratic is my new input for my second function, which is my f function. I distribute the two, combine like terms, and I end up at 2p squared minus 16p plus 27. So for today, what we are looking at is how do we determine whether a function is one-to-one. So we're looking at one-to-one functions. A function is one-to-one. Here is the notation that I'm going to use, 1-1. If every element in the range corresponds to exactly one element of the domain. What we are going to be looking for is the range doesn't repeat when we are dealing with one-to-one functions. Graphically, if we test whether a function is one-to-one, if its graph passes the vertical line test and also the horizontal line test, that means that the function is one-to-one. So the first part here, vertical line test, takes us back to, is it a function? If it passes the vertical line test, we have a function. So we always have to check, is it a function first? If it's a function, then we can move on to the horizontal line test, and this test is showing us that one-to-oneness. So is it a one-to-one function now? So you must start with the vertical line test and then the horizontal line test. There is an algebraic test for these, and this is the one that we like doing at this level. A function f of x is one-to-one if for a and b in its domain, f of a equals f of b implies that a equals b. So what does that mean? What we are going to start with is this piece. F of a equals f of b. We're going to input our inputs here, a and then b, do our algebra, and if we are able to prove this piece, a equals b, then that means that we have a one-to-one function. So not all functions are one-to-one. Some functions obviously aren't, and we're not going to be able to prove that. So that's the algebraic method. So let's go back to some basics. For example 1, we are determining whether the function is one-to-one. So for number 1, we have determined if the following relation is one-to-one. First of all, is this a function? So that's the first question I want to ask myself. If it's a function, the x values will not repeat. So right now I have a function, right? That's the first thing I want to always look for. So we have a function. So first step is that must determine, is it a function? Second step is this function now one-to-one? And what you're going to be looking at is the range, the y values. Looking at all of these y values, we can clearly tell that the y's are not repeated, which tells me that this is a one-to-one function. So I'm going to say these three dots represents therefore. So therefore we have a one-to-one function. Why is it one-to-one? Because the range does not repeat. Okay, let's look at number 2. Same process. First thing I want to determine is it a function or not? So I'm looking at the x's. So I have my g of x function. The domain does not repeat, so we have a function. Since it's a function, now I'm going to look more closely and determine if it's one-to-one. And I already see an issue here. That 14 is repeated. Since that 14 is repeated in the range, that means that we do not have a one-to-one function. So I'm going to say, therefore, not a one-to-one function. So let's look at our next example. For number 3, we're graphically looking to see whether we have a one-to-one function. So first thing I am going to determine is this a function? We have dealt with quadratics since algebra, and we know that all quadratics are functions. It passes the vertical line test. So here's my vertical line. Doesn't matter where I put this vertical line, my function only touches that vertical line once. So I have a function here. Now I'm going to determine, is it one-to-one? And the way we determine if it's one-to-one is by looking at the horizontal line test. So if I were to draw a horizontal line anywhere on my paper, I can see that I have issues. This horizontal line touches the graph twice, which means that the range is repeated. Over here, same thing occurred. It touches the graph twice, which means that the range is repeated. If the range is repeated, that means that, therefore, not one-to-one function. So here we have a function, but it's not one-to-one. For number 4, given the following, we got f of x is equal to 3 minus 2/3 x. A wants us to sketch the graph of f of x. So when we're sketching, we're rough sketching it based on what we see on our calculator. So I'm going to input this into my calculator. I already know what type of function it is because it is a function. This is a linear function. Just by looking at the equation, I automatically know that, and I'm hoping that you guys also notice that right away. So for part A, here's my rough sketch. I would start at 3. I'm just putting in that positive 3 as the y-intercept, and I know that it has a negative slope. So it'll look something like this. There's my rough sketch. For part B, we want to determine if f of x is one-to-one. So for part B, first things first, is this a function? Obviously. So we do have a function here. Is this function one-to-one? And again, I'm going to do my test here. If I do a horizontal line anywhere on that graph, we see that we are only touching that line in one spot, which means the range does not repeat, which is telling me that this is a one-to-one function. Okay, so first thing you must tell me, is it a function? If it's not a function, automatically you don't even look for one-to-oneness. But if it is a function, then you can look for that one-to-one piece. All right, let's look at some algebraic approaches. For number 5, what we are looking to do is algebraically determine if the following relation is a one-to-one function. So we have f of x plus 2x equals 4. First thing I'm going to do is make it in terms of f of x equals, right? Solve for y, solve for f of x, since that's what we have here. So I'm going to subtract 2x from both sides, and I will have my f of x is equal to negative 2x plus 4. So here we have a line. I have a line which is telling me that this is a function. So I could either graph this on my calculator and look to see if it's a function by its graph, but I know that a line is a function. So I'm not even going to do that. So here's what you're going to start off doing. So in order for this to be a one-to-one function and to show this algebraically, what we want to show is f of a equals f of b. That's our goal. But before I do that, what I want to start off with is, what would f of a be? Well, this f of a means that a would be the input. So wherever I saw an x in my original function, I'm just changing it to an a. So we would have negative 2a plus 4. And the same thing for f of b. What that b is telling us is that's our input. So instead of writing an x, I would write a b. So we would have a negative 2b plus 4, right? This is kind of like our extra step right here. So now that I have that, all I'm going to do is substitute into f of a equals f of b. So f of a is negative 2a plus 4. and we're saying equals f of b, which would be negative 2b plus 4. Our goal is to have a equals b. If I end up at a equals b, and if I could prove that, that means this is a one-to-one function. So what would I do? If I was solving this, we would say minus 4 on both sides. And what happens there? That cancels out. So I'm left with negative 2a equals negative 2b. My goal, again, is to get a equals b. What can I do now? If I divide both sides by negative 2, I'm able to cancel those out. And I'm left with a equals b. Since I am able to show a equals b, that means that this is a one-to-one function. So number 6, same kind of process. We have algebraically determine if the following relation is a one-to-one function. We have f of x equals x squared plus 2. I don't need to solve for f of x. F of x is already by itself. I have a quadratic, so I will quickly put this into my calculator just to see how this quadratic looks. And my function should look something like this. Okay, so I put that on my calculator. I see my quadratic. I know this is a function. Since I know it's a function, then I could actually do this process. So I am going to do my f of a and my f of b piece. So f of a in this case would be a squared plus 2. F of b would be b squared plus 2. Again, don't forget, you're just replacing the original x's. I'm going to set myself up. If this is a one-to-one function, then I have to start with f of a equals f of b. I'm going to substitute. F of a is a squared plus 2. F of b is b squared plus 2. I'm going to solve for a equals b. That's my goal. I want to get there. So let's see what happens. So if I were to solve this, I would start off by minusing 2 on both sides. And that would knock out the 2's. I would be left with a squared equals b squared. So I'm almost there. I want to try to get a equals b. So right now I'm looking at that exponent of 2 and I want to get rid of it. How can I get rid of that exponent of 2? The only way to get rid of it is to square root both sides. Okay, if I square root both sides, I am able to cancel out that exponent. But you have to be super careful here. I'm going to ask a quick question. What is the square root of 4? What would you answer? I know you would tell me it's a 2, but the square root of 4 is also a negative 2. So the square root of any number, doesn't matter what it is. Square root of 9, positive 3, also a negative 3. The square root of any number is always positive and negative. So we have positive and negative a equals positive or negative b. So I'm running into a little issue right now because let's say I have positive a equals positive b. If positive a equals positive b, then we pretty much proved the case of one-to-one, a equals b. But there's a lot of different things happening here. What if a was positive and b was negative? So this was good, but right here I'm not able to prove that one-to-one. What if I had negative a equals negative b? Again, that would be true because if I divide both sides by a negative 1, I end up at a equals b, which is what we wanted. But what happens if I have negative a equals positive b? Then again, I'm not able to show. Since I have this situation occurring here, I am not able to show that one-to-oneness. So I have to conclude that this is not a one-to-one function. And the reason I'm able to show that or prove that anyway is because of this piece right here. Once I had that piece, all of this occurred. And because all of that occurred, I had sometimes it came out true, sometimes it didn't. I'm not able to prove it always true. And that's what I want to do. And if I think back to what we did in the quadratic question, it's not going to pass the horizontal line test. So I already knew it wasn't going to be one-to-one just by its graph. Last one. So for this last one, we have an absolute value function. And let's just think about this, right? Again, I usually like to quick sketch these just to see how it would look. And if by looking at its graph, I already know the answer. Again, there's my rough sketch. It's an absolute value function. I know it's a function, but I could clearly already see that it's not going to pass that horizontal line test. So I already know it's not one-to-one. And here's the proof to it, the algebraic proof. So let's start with, since I have a g function, I'm going to say g of a and g of b. I have the absolute value of 2a minus 7, the absolute value of 2b minus 7. So I'm naming it based on its original name, which is the g function. I know that I want to prove g of a equals g of b, and my goal is to get to a equals b. So I'm going to substitute. All right, so the awesome thing about the absolute value is that two situations happen. So here are my two cases. There's two cases here. If I take out the absolute value, I could have case one of whatever was inside the absolute value comes out exactly the same, right? That's my case one. Case two, the first piece comes out, but the second piece gets negated. So that's my second case. So we always have two cases. Let's start with that purple one, the first case. If I were to solve the first case, I would add 7 to both sides, divide by 2 on both sides, getting me to my destination that I want, which is, it is a one-to-one function. Let's see what happens in the second case. If I try to prove that second case, first thing I need to do is distribute that negative to the parentheses. So I would have, and I'm going to combine like terms, like I would, right? I would do plus 7 on both sides. That doesn't help me out. It's not canceling out anything. 2a equals negative 2b plus 14. All right, let's get rid of that 2 in front of the a. And I would end up at a equals negative b plus 7. I'm never going to be able to show a equals b in this case. At this point, I'm just going to stop. And I already know it's not one-to-one. Since I'm able to show one, but not able to show both of them, I have to conclude that this function is not one-to-one. And just by looking at its graph from the start, I knew that was going to happen. So it was going to be impossible for me to prove that a equals b. So keep learning and keep growing, and I will see you in our next video.